My name is Professor Prof Orata, and we are continuing with our lecture series in thermodynamics. We have looked at Carnot circle, Rankine circle, other thermodynamic concepts and processes, and we now want to work out a specific example. We had done the Carnot efficiency and Rankine efficiency. So let us solve a particular example so that you have a practical grasp of what we are talking about. Let us first of all start by having our problem. And our problem says consider a steam power plant. Consider a steam power plant where the boiler pressure is 40 bars. And the condenser pressure is 0.04 bars. So first of all, before you start solving this type of problem, you must be sure that you get your unit correct. And number two, we are going to deal with the steam tables. The steam tables, so we want to talk about units. Then we are going to deal with the steam table. And these steam tables will give you the values of saturation pressure for steam. Saturation pressure for steam, table for steam. It will also give you saturation temperature. Let's write it out, table for steam. For steam. It will also give you superheated vapor table for steam and compressed So that's the gist of the steam tables. It will give those saturation pressure values, will give you saturation temperature values, it will give you the superheated vapor values and compressed liquid values. So one of the first things which we need to look at is we have talked of the boiler pressure being at 40 bars and the condenser pressure being at 0.04 bars. Now, as you're talking, let me just remind you, and it's good to know this, that 1 bar is equals to 10 to the power 5 pascals. Remember, bar is a unit of pressure. So 1 bar is 10 to the power 5 pascals. So when you go to the steam table, you get those values normally in this one. You need to put them in kilopascals. So we need to convert 40 bars for the boiler pressure to pascals, and we need to convert the 0.04 bars pressure for the condenser to pascals, kilopascals. That means whatever you get the value for pascals, we will divide by 1,000 to give us the kilopascal. So 40 bars will be equal to 40 times 10 to the power 5 divided by 1,000, and that will give us 4,000 kilopascals. And 0.04 bars will be 0.04 times 10 to the power 5 divided by 1000, convert it to the kilo matrix, and that will be 1, 2. So that is 1, 2, 3. So we'll have 4 kilopascals. Now, we now go back to our Carnot circle. We now go back to our Carnot circle. And remember, we said that the efficiency, let's just draw the Carnot circle, just to remind ourselves, the Rankine scale, the saturated vapor, always remember, line, saturated liquid line. This is temperature, that is entropy, so we have highest temperature and the lowest temperature, and this, let's call the state points 1 to 2, 3 to 4. This is the boiler, this is the condenser, turbine, condenser, pump. And we are saying that the boiler pressure is 4,000 kilopascals. Condenser pressure, we have said, is 4 kilopascals. I repeat, that is the Rankine circle. That's the Carnot circle in the Rankine matrix. That's temperature versus entropy. So we have the boiler pressure is as 4,000 kilopascals. The condenser pressure is as 4 kilopascals. And normally the boiler pressure is high. And to make it even more efficient, you increase it. If you look at our discussions on the supercritical Rankine cycle, you will remember that. Then the condenser pressure is normally very low. So we want to first of all find from the steam table the corresponding temperatures for the pressure when it's at 4,000 kilopascals and when it is at 4 kilopascal. And if you go to the steam tables, you will find that the temperature corresponding to the 4,000 kilopascal, the temperature from the steam table is 523 Kelvin. And for the 4 kilopascal, the temperature from the steam tables, not that, so don't worry, don't wonder where this has come from. You have to go to the steam tables, go to the saturated pressure table for steam, look at 4,000 kilopascals, you'll find the temperature there. In fact, you'll find the temperature there is 523. There is in the first column, and for 4 kilopascals, you will find it is 302 Kelvin. And in that steam table, there will be values for enthalpy, and there will be values for entropy and values for internal energy and so forth. Very important reference unit. Now, so we can calculate the efficiency. Remember, we said the efficiency for the Carnot circle we found was 1 minus Tc over Th. So straight away, we can plug in those values so that we have that efficiency now is 1 minus 523 over 302. That gives us 42.3%. If we remove the percentage, then it is 0.423. Now, so what is the total work? We want to compute the total work. So this was the initial quantities which you have. Now let us compute the total work. And the work. So remember, from the Carnot circle, we have said that this efficiency in terms of the changes in enthalpy, because we said for first law, the first law of thermodynamics for steady state flow processes, where the kinetic energy is assumed to be zero, where the potential energy is assumed to be zero, and where it is adiabatic, then dH was minus dW. This is from first, we said, from first law of thermodynamics for steady state flow process. And so, in a nutshell, we are talking of, when we are talking of the total work, W total, we are basically talking about efficiency times H1 minus H2. Because the boiler is what we consider as the input, and whatever we get out of the turbine minus the work input in the pump is what we consider as output. And so we can multiply with our efficiency, that is 0.423 to H1 minus H2. That's the enthalpy, state point 1, state point 2. State point 1 and state point 2. Now, how do we obtain these enthalpy values? If you look at the Carnot circle transposed on the Rankine axis, temperature and entropy, the enthalpy value at state point 1 corresponds to the enthalpy for the liquid. And the enthalpy at state point 2 corresponds to the enthalpy for the gas. And these values of enthalpy, we will get them again from the steam tables at 4,000 Kelvin, 4,000 kilopascal, 4,000 kilopascal. So go to your steam table, look at the saturation pressure at 4,000 kilopascal, and then you look at those columns. You'll see a column with HF, that's for the liquid, and HG for the gas. For the gas. And you'll find that at 4,000 kilopascals, at 4,000 kilopascal, we find that HF is equals to 1087.16 kilojoules per kilogram. Those are the units of enthalpy. And for the gas, Hg, we have 2801.9 kilojoules per Kelvin. I repeat, these are values which you get from the steam tables. And so W total, which I call T, will therefore be the efficiency, that's 0.423 into 2801.9 minus 1087.16 kilojoules per kilogram, and that equals 725 kilojoules per kilogram. That's the total work. So I repeat, these values, you get them from the steam tables. Steam tables will give you saturation pressure for steam, saturation pressure table for saturation temperature table for steam, superheated vapor tables for steam, and compressed liquid values for steam. Now, what about for the turbine? What about for the turbine? Let us do something there. I don't want to remove this particular diagram so that you are always remembering it. Now, what about for the turbine? Let's look at the turbine. W turbine, the work done by the turbine, remember it is from state point 2 to 3, therefore the turbine will simply be H2 minus H3 minus H3. Now, notice one thing, that the H3, the state point for H3, does not touch the saturation vapor curve. So how do you go about it? We don't have that value. So how do you go about it? Now we capitalize on the fact that we said this was an isothermal process, state point 1 to 2, process 1 to 2 is isothermal, process 2 to 3, we said was isentropic. Isentropic. So entropy is there. So we can use the value for entropy because if we know the value for entropy at state point 2, we will know the value of entropy at state point 3. And we will get moving. In the same way, we have the condenser here. State point 4 does not touch that saturated liquid curve. No. So again, but we know that this process is adiabatic from 4 to 1 and it's isentropic. So again, the entropy at S4 and S1 are the same. So entropy is another state function, thermodynamic state function, and there are relationships between these functions. So we can use that. So because we cannot, we don't have the value for H3, no value for H3. Therefore, we use the fact that it's isentropic. Therefore, S2 is equals to S3. So let us proceed by working the entropy. And this, the units are in kilojoules per kilogram per Kelvin. Note that for entropy S, the units are in kilojoules per kilogram per Kelvin. So now we can move to get our solutions, given that we know that there's a thermodynamic relationship involving this isentropic process. So let us see how we do that. So we know that we can find the value of S2 from the steam tables. We can get the value of S2 from the steam table. So obtain the value of S2 from steam table, because you know the saturation temperature. So you can get the value from the table. And what does that correspond to? So we are talking of the entropy, the gaseous form. This is at the liquid form. So S2, same as Sg. So we look at that at 250 degrees centigrade. Remember when we had 273, here we get 312,523 K, which is what we used. Remember, we used it in Kelvin. In the steam table, you will find it there. You look at it, you must look at what are your temperatures. What temperatures have been put there? Is it Kelvin or is it degrees centigrade? So that you get your correct information. So we will see that this value at 250 degrees centigrade, the value for that quantity for the entropy is 6.067 kilojoules per kilogram per Kelvin. And also the other important thing to note is that from the steam table, when we go to the entropy, when we take the tangent of going to the entropy rather than enthalpy, we will get values for entropy at 4 kilopascals. We will get values for entropy at 4 kilopascals. We get the value for entropy at 4 kilopascals. And these values are there. So we are saying that from steam table, I want you to note, from steam tables, you can obtain entropy SF and SG at 4 kilopascals. That's at our lowest temperature there, 4 kilopascals. And these values are given as follows. The value of SF at 4 kilopascals is 0.4225 kilojoules per kilogram per Kelvin, and SG is 8.47 kilojoules per kilogram per Kelvin. Please make sure you look for these values yourself individually from the steam tables. Make sure you do that. Look at them. You can vary now, for example, you can choose to vary this pressure at some point. Now put it at 2000, put that at about 2 kPa, and repeat the calculation. Again, vary it, repeat the calculation so that you are familiar with these things. You get used to them. You get used to them and they become part of your thermodynamic thinking. Now, we have those particular values. And there is another very important concept, that is, so if we want the enthalpy for S3, we will use an important concept which deals with basically mole fractions. For example, if you have the mole fraction of one of two species, X1, X2, liquid and vapor, for example, then you will find the total is always 1. And so, in other words, X1 is equals to 1 minus X2. And so, we can bring this into the thermodynamic format so that if we have, for example, H, then we can have HGX plus HF into 1 minus X. So that if the mole fraction of one of those phases is X, the other one must be 1 minus X. And so if we open up this quantity, we have H is equals to HGX plus HF minus HFX. And of course, factorizing out the Fx, we get HF plus X into Hg minus Hf. And this Hg minus Hf, we normally write it as HgF. We normally write it as Hg. Let's get that. We have X into Hg minus Hf. So we arrive the right track. So now, using this identity, that is Fg, using that identity, so anytime you see HFG, you know it is simply Hg minus Hf. Always note that. So using this thermodynamic relationship, let's use part of the board. I still need this diagram as you do the explanations. Then we can say that for S3, so for S3, that's at point 3, we can now obtain the entropy at point 3 as being SF plus X into Sg minus Sf. So we can put in values. Again, for you must look from your steam tables to see those values. I said you vary the pressures and keep working with them throughout and see what you get. So we had said that, where were we? We had said that for S3, so we can use values here. That is S3, we can use our values. Remember, S3 was equal to S2, and for that value, we can get that value for state point 2 at 4,000 kilopascals from the steam tables, and we know that it is equal to the value, because it's an isentropic process, S2 is equals to S3. So when you have the value of S2, that's the value of S3. And that value is 6.067 from the steam tables. The value for SF at 4 kilopascals will be 0.4225 plus X into 8.47 minus 0.422. This, if we simplify it further, then that value still becomes 6.067 is equal to 0.4225 plus 8.053x. So that the value of x, just subtract that from there, 6.067 minus 0.4225 divided by 8.053. And that gives us 0.704x for the value for x. Very important for us to note that. So you just work on the things systematically. I said, we don't have H3, but we realize that's an isentropic process. We can get the value of S2. And so if you get the value of S2, we know that's equals to S3. If you get the value of S1, that's the same as the value of S4. And we proceed. And this is a thermodynamic relationship. So we are going to move that direction. We have calculated X there. Then now we will go to use that thermodynamic expression for the enthalpy. We use that for the enthalpy. So let us see how we get there. We use that for the enthalpy so that H3, therefore H3 also will be equal to HF plus X H into FG, which is simply H3 is equal to HF plus X into HG minus HF. We know the value of X, we have already computed it, so we'll be able to use it. And so if we go to the steam tables, then we will find that H3 will be, the value for HF will be 121.38. Remember, 38 at 4 kilopascals, HF will be 121.38 plus 0.70. Remember, this is our X value, which we have gotten here, into 2433.6. That will give us H3 as being equal to 121.38 plus 17,083, which will be equal now to 1824 kilojoules per kilogram. Remember now, this is enthalpy. So it's not kilojoules per kilogram per Kelvin. No. Make sure that you are very, very conversant with your units. Therefore, for the turbine now we know what it is. So W for the turbine, which is simply H2 minus H3, is now equal to the earlier value which we got, 2801 minus 1824, the value which you have just gotten, and that gives us 977 kilojoules per kilogram. That'll be for the turbine. Now, remember for the compressible work, because remember we talked of the work output as being W turbine minus W pump. So we can actually get that for the pump by simply saying W total was W turbine minus W pump. And so We have those values already. 725 minus is equals to 977 minus WP, therefore, is equals to 252 kilojoules per kilogram. So all you need to do is do it very, very systematically. Make sure your units, you are not talking of 40 bars and the units are in kilopascals, and then you just go there and instead of converting to kilopascals, you take the 40, put it there, so it's like 40 kilopascals instead of 4,000 kilopascals and so forth. So you make sure that you are keen as you do the work, and also I base your arguments on thermodynamics. Like we have said, you can't get H3, but we know in terms of entropy that 2 and still 2 and 3, the entropies are the same. That's because it's an entropic process. We know, for example, temperature 1 and temperature of 2 is temperature of 1 is equals to temperature of 2. So if I know temperature of 1, I know temperature of 2, because that's an isothermal process, and so forth and so forth. So one needs to be a bit cautious. Let us now look at the next calculation, which is specific steam consumption from let's look at specific steam consumption. But before we do that, we just remember that work ratio, which is a very important quantity, work ratio denoted as WR, is equals to W total over W of turbine. A very important quantity, and that quantity there from our values is 725 divided by 977, and so the work ratio is 0.74. Now, the last parameter which you want to compute is the specific steam consumption value, what we call SSC, steam consumption value. And that is the amount of steam consumed per kilowatt hour. And so, very, very simple, that steam consumption, SSC, is steam consumption per hour divided by the net power output. Net power output. Now, I want you to also always remember that a kilowatt hour is an energy unit, and it is 3.6 megajoules. Kilowatt hour is an energy unit, and it is 3.6 megajoules. Let's just note that. At a kilowatt hour is a unit of energy, equal to 3.6 megajoules. In other words, 3.6 times 10 to the power 6 joules. Kilojoules is times 1,000. Megajoules is times 1,000,000. So we can have megapascals. For example, the critical temperature of water is at about 220 megapascals. If you look at the other lectures which we have covered. And so what do we have here? So now we don't need that. We can now do our SSC, our steam consumption. Therefore, will simply be 3.6 megajoules divided by 725 Remember, our 725 was in kilojoules per kilogram. So we multiply 725 by 10 to the power 3, and that will give us 4.79 kilograms per kilowatt hour. Very important to do this calculation. Like I said, now vary, for example, your temperature. You can vary your pressure in your diagram. You can vary your pressure, like I say, so that you practice with it. They say that put the temperature like that. Take, for example, that this is at 50 kilobars, 50 bars, and let's say this is at 0.05 bars. And repeat the same exercise again. Then probably now put it at 30 bars, and this at maybe 0.03 bars, because this temperature entropy, and see what it is, and see what pattern you pick out of that. But remember, you will see that efficiency of the boiler increases as you increase the pressure, and efficiency of the condenser increases as you decrease the pressure. So thank you. We are continuing with the lecture series.